Все, это тоже работает, да, для докладчика?
Ну да.
So, good morning, ladies and gentlemen. I would like to welcome you on the second day of Terahertz Symposium. First of all, we would like to thank all our sponsors, not only for this Terahertz Symposium, but for the conference. You can see all the logos on the screen. The first speaker today is Petr Obraztsov from Prokhorov General Physics Institute, Russia, and I would like to invite him to give a talk about terahertz emission from hybrid perovskites. So you have around 25 minutes and then several time to questions.
Okay, thank you, Marie, for introduction. And first of all, I would like to thank organizers of this very nice symposium for inviting me here and to make a presentation about our recent results on terahertz emission from different materials. Actually, the topic which I would like to talk today about is the terahertz emission from hybrid perovskites. However, I decided to slightly broaden the topic, and I will also tell a little bit about terahertz emission from different layered materials, such as graphene and topological insulators, which in my opinion are really are tightly connected to perovskites. So this work was mainly performed in Prokhorov General Physics Institute in Moscow in laboratory of laser spectroscopy. However, I will talk about several experimental results which were done in collaboration with different groups from University of Eastern Finland, University of Tokyo, and also the samples were provided by people from Novosibirsk. So here's a short outline of my talk. First, I'll give a short introduction and tell a little bit about methods to generate ultra-fast photocurrents and terahertz radiation in different solids, and about methods to detect induced photocurrents by measuring the real photocurrent response and terahertz emission, terahertz response. Then I'll tell about our previous experiments on polarization-dependent photocurrent generation and terahertz emission in different 2D and related layered materials, which became a motivation to study our perovskite samples. And later on, I'll go to our most recent results on control over photocurrent with polarization of light and terahertz emission in MAPI samples. And finally, I'll conclude my talk and tell a little bit about new perspectives to use these materials. So here I show a photo of one of the setups. Actually, this setup is situated in University of Tokyo. You can see here many different terahertz setups. For example, this one is time domain spectroscopy setup, which we use to study topological insulators. So I'll just briefly remind you some methods to generate photocurrents. I divide them into two parts. First is, I call them conventional methods, which includes methods based on Schottky barriers, p-n junction, external biasing. These methods are good, but all of them require external action on the material properties. And also p-n junction photocurrents are limited by thermodynamic limit. So another quite popular method to generate photocurrents is based on quantum interference of 1 and 2 photon absorption pathways or frequency mixing. However, these methods are third order nonlinear optical processes and they have very low efficiency, require phase matching, and of course they require very high intensities, often comparable to the material damage threshold. Another method is photodamper and photothermal effects, which requires non-uniform illumination and engineering of thermal and electronic properties of materials. So all these methods do not provide information on intrinsic material on intrinsic electronic properties of material which we want to study. So we cannot use this method to understand real carrier dynamics, or if we want to study electronic band structure. However, there are some alternative methods. These methods can be united by the name of bulk photovoltaic or anomalous photovoltaic effect, and these methods are completely different from the conventional ones. Here the photocurrents are generated directly by, so the carriers are driven directly by photons. For example, these effects include photon drag effect, which is direct transfer of photon momentum to, let's say, electron, or to the charge, or linear and circular photogalvanic effects. Just a little bit more about photon drag. So as I already told you, this effect is actually this effect is known for a very long time, and it is based on momentum transfer. And in principle, these photocurrents can be observed in any medium. These photocurrents are ballistic by nature because they do not because they are related to momentum relaxation time, and which is very important for us here. These photocurrents are sensitive to the k-vector direction. So this is a good way to distinguish these photocurrents from any other. However, these effects are, in conventional materials, these effects are have very low intensity, and very hard. It is very hard to observe them. Another type of photocurrents are photogalvanic currents, which originate actually from spatial charge transfer during the transition from valence to conduction band. These effects require some asymmetry of the sample, and they cannot be observed in medium with in centrosymmetric medium, and require some non-center symmetry. Okay, so how to detect these currents? The simplest method is just to apply conductive electrodes and to measure the photocurrent directly by measuring the voltage drop across these contacts by using oscilloscope or some other ampermeter or voltmeter. However, these methods have low temporal resolution and provides only time integration signal. These measurements are very sensitive to slow effects, and also by applying additional contacts to the sample, we induce, for example, band bending around the contact area or some other contact effect. So again, this is not good to get information on carrier dynamics. However, I'm coming to this the topic of this symposium. So there is another method which all of you know very well. We can measure these photocurrents by emitted terahertz field. Actually, these methods have really good advantages. So it's sub-picosecond temporal resolution, information on both amplitude and phase of the current and do not feel slow effects. So this method provides direct access to excited carrier dynamics. Here are the methods and types of photocurrents. I will now show our experiments on generation of this type of photocurrents first in single and multi-layered graphene, and later on in topological insulators. So here are the transmission spectrum of the samples we use. And we start from measuring real photocurrents by the methods with contacts. So first we were able to obtain polarization-sensitive photocurrents, which we relate to photon drag in graphene. These photocurrents demonstrate very nice, very pronounced dependence on polarization of excitation. And as I told previously, these photocurrents are sensitive to the K vector. So by shining our sample from one side or another side, we can produce photocurrent of opposite polarity. So having these results, we decided to apply Terahertz emission spectroscopy. And by measuring both components of emitted terahertz field, we can retrieve the terahertz polarization and actually the trajectory of the charge in plane motion of the charge. So we apply femtosecond excitation incident at some, let's say, 45 incident angle, and generate photon drag currents, which produce quite efficient terahertz signal. So again, nice polarization dependence in agreement with photon drag current was observed, and these photocurrents were interpreted in terms of this phenomena. So let's now move to a more complicated structure, which is topological insulator. Before I was talking about graphene, which has a Dirac-Kohn electronic band structure. In topological insulator, the situation is a little bit more complicated. So the surface states again demonstrate Dirac-Kohn band structure, but in the band of material, in the bulk of material, this traditional narrow band semiconductor. Moreover, there is spin splitting due to efficient spin-orbit coupling in these materials, and one branch and electrons having opposite spin directions are sitting on different branches of band structure of the band. Or in other words, electron, due to this spin locking, electron moving in the right direction will always have opposite spin comparing to electron moving to left direction. And there is a reasonable question how to separate optoelectronic properties related to the bulk and surface. In 2012, it was suggested that by measuring this helicity-dependent photocurrent, it is possible to separate this contribution. So, indeed, if we observe some polarization, some photocurrent which is dependent on helicity of light, we can say that this current is related to the spin-splitted surface states. And the photocurrent which do not feel this helicity of light should be related to the bulk structure. Since that time, many contradictory reports were published. Some people were observing this helicity dependence, some not. But in our experiments, we employed different samples of topological insulators, namely bismuth selenide and bismuth telluride crystals. Their surface states were confirmed by ARPES measurements. So here, nice Dirac cones can be clearly seen. And so we employed terahertz emission spectroscopy. First, we measure the power. We perform the time-integrated measurement with just by using Galilei cell and obtain the dependence on both helicity of light and rotation of linear polarization. And later on, we moved to time domain spectroscopy. So here are the typical time domain waveforms and terahertz spectrum obtained from this, actually from this bismuth telluride sample. And by tracking the amplitude of terahertz peak, we can observe these nice dependencies on polarization, and you can clearly see that the amplitude of the signal obtained under excitation with right circular is different from the left circular. So these results are in agreement with both photocurrents, photocurrent measurements, and can be interpreted as a circular photogalvanic effect. So we demonstrate that terahertz emission spectroscopy is a very powerful tool to get access to the electronic band structure of material. So having these results in mind and having these setups to study actually layered materials, we moved to another type of materials, which is now very prospective, mainly in terms of low-cost printed solar cells. Those materials are hybrid perovskites, and actually in our studies we use the most popular and benchmark perovskite, methyl ammonium lithium iodide. This why these materials are interesting. First, they provide very cheap and easy processing way to produce very high efficiency solar cells. They provide high absorption in visible range and long carrier diffusion lengths, which is actually important for our experiments. However, many aspects of these materials are still debated or even unknown. What is the symmetry? No actual, no complete understanding of the carrier dynamics. If there is spin splitting or not, what are the mechanism of photocurrent generation, and finally, is it possible to use this? Is it possible to somehow enhance the efficiency of these materials? During the last 2 or 3 years, many works were published on mainly theoretical works on calculation of bulk photovoltaic effect in this material. Actually, this effect could provide a way to enhance the efficiency and to obtain the efficiency over the thermodynamic limit. One of the theoretical papers were actually focused on on calculation of circular photogalvanic effect in MAPI samples, and they related to symmetry broken due to spin splitting in this material. So here is the photo and the picture of the samples we use in our study. So we employed the material prepared in a way traditionally used for fabrication of real solar cells. Only some parts, so it is not actual solar cell, but we just do not add additional layers here. But in principle, this sample looks like solar cell. So here are some typical characteristics of this material. Actually, this polycrystalline film with 350 nanometer thickness. And okay, the efficiencies obtained with this particular material of the solar cell are they are rather not very good, but okay, let's say they are okay. It's about 13%. It's less than the record ones, which are about 20%, but still they are okay. And again, we use this material to generate photocurrents using the methods which I told you before. Actually, it's a very similar setup to that one we used to study other materials. And again, we can obtain the photocurrents which demonstrate clear dependence on both linear polarization, especially it can be seen in transversal geometry of experiment, and helicity dependence. So the overall photocurrent response can be described by this in this way. So where D term is a photodember effect or photothermo effect, which is polarization insensitive, and these coefficients corresponds to circular and linear photogalvanic effect and photon drag effect, which we are actually interested in. So we apply different wavelengths to excite these photocurrents, and can clearly see that the contribution of different type of currents strongly depends not only on polarization but also on the wavelengths. And now I move to terahertz emission experiment. Again, we use pretty similar geometry. However, we have to use second harmonic to excite our sample because of because of special absorption spectrum of this material. We use traditional TDS system to detect this radiation. And here is the typical time domain waveform and spectrum of the emitted terahertz radiation. So this was the first demonstration of terahertz emission from hybrid perovskites. And we demonstrate that the efficiency of terahertz emission strongly depend on helicity of light, which is direct evidence of circular photogalvanic effect, or let's say bulk photovoltage. So now I come to conclusions. Terahertz emission spectroscopy provides very sensitive tool, very sensitive and non-destructive tool for surface and interface analysis of advanced materials. Ballistic by nature shift and injection photocurrents may enable perovskite solar cells with higher efficiency, and this results on terahertz emission open new opportunities for perovskites to use perovskites in spintronics and, for example, terahertz photonics. I would like to thank all collaborators and co-authors of this work from these organizations. Thank you.
Thank you. Let's send our speakers. So questions?
Hello. My questions about perovskite. What terahertz amplitude dependence of intensity of laser do you have?
Actually, it's linear dependence.
Linear?
Yes.
to what intensity?
So it's comparable. The signal is comparable to the one obtained from another material. So it's also
Average intended power.
okay. This material is very sensitive, so the damage threshold is quite low. So if we focus more, we can just burn a hole in the sample. What exactly what fluence we use here, so we were working at quite low intensities. And trying to, it strongly depends on exact sample. I mean, on particular sample. If we use a thicker film, it will absorb more, and therefore this threshold will be higher or lower. Or yeah, that's it.
Thank you.
Any other questions? Okay, let's thank speaker again.
Thank you.
So, and the next speaker is Andrei Gorodetsky from Imperial College of London and ITMA University, and he will give us a talk about applications of terahertz time resolved spectroscopy to study the photoconductivity of lead halide perovskites.
I'm going to talk about pretty much similar studies of carrier dynamics in perovskites, but not in the way of terahertz emission spectroscopy, but optical pump terahertz spectroscopy, and what further steps can be taken to get the more insights into the nature of the carriers, the carrier dynamics that are happening in these materials. This work has been done in Imperial College London, and we are quite a young group doing ultra-fast spectroscopy. This is some part of our setup. We're using different wavelengths, and we can do different techniques to study the carrier processes in different photoconductive and photovoltaic materials. We are a group in the chemistry department, but most of us are related to laser physics. So we are doing ultra-fast spectroscopy. We're doing normal pump probe experiments, which is like optical optical probe with different wavelengths, two-dimensional spectroscopy. When we use different wavelengths, when we tune both wavelengths independently, we're doing time-resolved photoluminescence. We have time-resolved terahertz setup. We're doing electroabsorption experiments, interferometric experiments in mid-infrared, and we do pump-push photocurrent. I will talk a little bit about this technique further. And we're doing 3-pulse experiment, which is pump, push, and probe. Again, I will show some results on this later. Overall, we covered the most part of the spectrum, starting from UV lights, like 300-something nanometers, up to infrared, up to 2.5 microns. Then we go further for mid-infrared radiation, where we cover the spectroscopy between 3 and roughly 8 micron, and we have a terahertz setup which covers the longer wavelengths, and we use these radiation to study interband and intraband processes in materials, and we use terahertz to study the photocurrents directly. So Perovskites are a hype topic now. As it has been mentioned, they are quite efficient. Current efficiencies overcome 20%, and they are regarded as quite prospective photovoltaic materials because they are quite easy to be in production. They are efficient, and all the other things that were mentioned in previous talk. And these are the samples that we were working with. We have slightly thicker samples. We use samples of roughly 600 nanometers, but again, it's non-structured layers. And the theoretical efficiency limit of the photovoltaic materials has been suggested in like more than 50 years ago. Some part of solar radiation is not absorbed by the materials. There are some extraction losses, and most losses will be regarded to thermalization. And actually, in our studies, we are looking into these losses when the electrons have this excess of energy that is lost through thermalization inside the material. So we are looking into so-called hot carriers that are pumped with wavelengths much higher than the bandwidth, and whether these carriers and this energy can be used before thermalization happens and dragged into photocurrent. So we look into materials and techniques to extract carriers before they cool down and lose energy. We look into characteristic times of cooling, how much time is needed to extract them, and the mobility in this hot state to discriminate the mobility of the carriers at hot states and colder states. So what is happening actually when it's when the sample is pumped with we're using lasers, but it will happen the same way under just a solar light. So the hot carriers are usually generated, since the band gap is usually about 600 or 700, correspond to 600 or 700 nanometers pump. So then two-step relaxation happens. The first step is thermalization, then it's cooling, carrier phonon exchange of energy, and then carriers are relaxing to the ground state. Mostly these studies most studies are being performed by just normal transient absorption when the sample is pumped with different wavelengths, and people measure the pump probe characteristic times and try to see the difference between carriers pumped at different wavelengths, and thus derive the effect of hot carriers versus cold carriers. Yeah, this is normal pump probe setup, and what's usually the visible beam is being used as a pump source, and some near infrared probe is probing it and is being measured. And what is happening is that we have the change of transmission, and then we just look at recombination and versus time and and we can derive the dynamics of carriers there. These are some typical curves, pump intensity dependent pump probe measurements, and we can see that at higher intensities we can see Auger processes at higher pump fluences that result in faster recombination times due to energy exchange between the carriers. But if we turn to terahertz transmission measurements in just a normal pump probe layout, this normal infrared pump probes, they would measure carrier concentration only. But if we turn to terahertz measurements, and terahertz transmission will be related not only with carrier concentration, but also with carrier mobility. So by direct comparison of carrier concentration derived from pump probes and carrier mobilities and terahertz measurements, we can derive carrier mobilities at shorter times after being pumped, and thus we can estimate and select better materials that reveal higher mobilities for hot carriers that can be extracted more easily before they are cooled down. Indeed, these are results for cesium-lead bromide perovskite. This is not this is inorganic perovskite, but it's not as efficient as previously mentioned benchmark MAPI, but still it gives some decent efficiency and gives some decent signal in both pump probes and terahertz. These are the curves, and we can see that terahertz probes indeed happens quite faster at the same pump fluence, which is and can be associated with a change of mobility, carrier mobility within cooling process, like that hotter carriers that would have higher carrier mobilities if compared to colder carriers. This is just the setup, which is a typical optical pump terahertz probe setup. The BBO crystal is missing, but we are pumping with 400 nanometers, which is well in excess of energy of the band gaps for all the perovskites that we are using. So the beam is split into pump delay and probe delay beams. Then we are using a large area photoconductive emitter, which we found to be quite efficient, quite nice trade-off between using. We are using amplified system, but the energy that is left for terahertz setup is not really high. So using a filament generation or other types of nonlinear processes would be not as efficient. But this is biased large area photoconductive emitter, and it's quite efficient and it's quite broadband to be employed in this setup. So and this is actual setup. This is an actual photo of the setup. So this is the incoming beam. Then half of the beam is being cut for the pump, which pump is passing through the BBO, and then there's some filters. And actually, yes, setup is quite compact because we suffered 2 lab moves within 1 year. So once the setup is built, after 3 months, we have to move the lab. And the second time I've built the setup, and another move to another campus was planned, so I built the setup on a breadboard so that I don't spend much time on further alignments. That's why it takes only 60 by 60 centimeters breadboard. So the incoming beam, the pump beam, is converted with BBO and pumps the sample, which is situated in the focal spot of the parabolics. Then the beam that's pumping the emitter goes through some extra delay for beam path matching, and is pumping the photoconductive emitter, and then terahertz is being collected by parabolics focused down with parabolics with shorter focal distance, and then coupled into zinc telluride for detection. And the probe beam is independently delayed and also the electro-optic detection is used to detect the signal. I'm not looking into the time domain curves for terahertz radiation, but these measurements are done in full 2D scan, where we scan both the terahertz field in time domain and we change the delay time for the pump beam. And while looking at this is just the amplitude at the maximum. it's not the spectral amplitude yet, but it's its amplitude of maximum of the terahertz pulse. We can see similar trends as we noticed in optical measurements, that cesium lead bromide would reveal much faster relaxation times than MAPI and FA for medium lead bromides, lead iodide. And if we look at the earlier times, we can see that the build-up is quite similar for all of them. And these are the maps that we get for, this is terahertz spectrum. This is change of transmission normalized to terahertz transmission. So this is change of transmission that is being induced by optical pumping. This is versus pump delay. So we can see that there are some characteristic frequencies can be noticed in the spectrum, and the characteristic times for some of the frequencies are different from the others. And I will look into this further. And this is just preliminary results as they've been obtained this about a month ago, and we are still looking into analysis into this. So if we plot the measurements, then we turned to more thorough study, more systematic study. We looked into bromides only, so we have methylammonium, formaminium, and cesium lead bromides, and we looked into the spectra. This is the change of transmission normalized to terahertz spectrum at different time delays at just after the pump. Maybe it's not really visible, but it's a yellow curve. Then 100 picoseconds after 600 picoseconds, and 1 picosecond after the pump. And the rate of change is slightly different. Like cesium reveals much lower change of signal; it's less than 1%, while at MAPI and at FA bromides we have the signal that is about the change of signal that is about 1%. This is again, the pump is about 36 microjoule per centimeter squared. And if we look at the spectra and temporal characteristics, and this, I believe this hasn't been reported, that we can see in some materials, for example, like cesium, at some frequencies the rate of the temporal constants of the by exponential decay, which is mostly used for these materials, differs twice between different frequencies, like 0.4 terahertz and 0.5 terahertz. The characteristic times would be 2 times different, which may be associated with different interactions happening within carriers and lattice or carriers of phonons, and we still need to analyze this more thoroughly to explain and work with theoreticians to build more of explanations for this. But this is quite repeated. We can see this in numerous measurements, and further we will see that cesium actually reveals stronger couplings that are measured directly. So yeah, this is the conductivity derived, and again the conductivity drops within time quite fast, and this is in good agreement with previous publications with these materials, so the photoconductivity in these materials. So, and then just a short flashback to the previous talk. These are the results for terahertz emission spectroscopy in I think this was MAPI as well. And what this was not the first demonstration, but the second, but they managed to publish it faster, I guess. And what they have shown is that they try to excite just above the MAPI band gap with 770 nanometers. And what they see in terahertz spectrum is that they have generation mostly at below 2 terahertz. And the dynamics for all the frequencies, the dynamics of, they do like short window Fourier transform where they apply a really short Fourier window across the time domain spec signal, and they can see that at different frequencies, the photocurrent at different frequencies happens at similar times. But when they pump at excess of energy at 400 nanometers, they have the strong peak at 2.8 terahertz, around 3 terahertz appears, and the short window Fourier transform reveals different dynamics of the current buildup, and that at lower frequencies it builds up faster, while the higher frequencies they just follow it, which shows the interaction of carriers of the hot carriers interaction with lattice, and this frequency is actually associated with this interaction. So we'll keep looking into this and keep analyzing the data, and actually we have a good set of materials to make a database and relate these characteristic times and to donors and different donors and acceptors in Perovskites. Just a little bit more about further steps that can be taken. We've recently published some results on actual direct measurement of hot carrier dynamics and hot carrier cooling in Perovskites. And what we actually do, we didn't change the pump photon energy. We pump with excess of energy, then we wait for some time till the carriers thermalize, and then we use infrared pulse, extra infrared pulse to just perform interband heating of these carriers. So, and then we measure the change of transmission. So what is happening here is that we have not just two pulses, we have pump and probe, but we also have a really powerful, another powerful signal, which we call push. And what processes are happening here? So first, again, we pump the samples, and we see the change of the drop of transmission in probe signal. Then the carriers are cooling up to some extent. Then the push pulse arrives. So once the push arrives, we can see the bleach of transmission, and then upon carrier cooling, the transmission just comes back to normal pump probe curve, and then follows normal relaxation process and recombination. This is just an experimental signal that we can see. This is optical pump infrared probe. This is not a terahertz measurement, but I'll talk further how can this be used. So first we pump at really low powers, not to have Auger processes, but we have excess of energy. So, and then when push arrives, we have a drop of signal, and then recovery of the signal to just to the normal curve. These points correspond to the same pump conditions with push and with no push, and we can see that the curve is just similar, and push affects only this part of the signal. If we plot the difference between these two graphs to reveal just the push dynamics at different push intensities, which correspond to different concentration of hot carriers, we can see that we can reveal the dynamics and fit it with exponential processes. And what we have noticed is that the higher, the more hot carriers we have, the longer they would cool down. These are the times. It's sub-picosecond process. So at lower push intensities, it's around between 100 and 300 femtoseconds. But at higher push intensities, it goes up to maybe even 1 picosecond. So we did a thorough 2D scans, like changing the power of pump radiation and changing the power of push, and looked at different materials like Fe bromides, iodides, and different acceptors. And all of them have this trend of cooling time elongation, but an inorganic cesium lead bromide has the highest rate of the cooling time elongation with push intensity. So if we plot the slope and the intercept time, these will be the dependencies, and cesium has significantly stronger dependence on hot carrier concentration. These data would be consistent with most reports, but this was the first direct measurements of hot carrier cooling, so we published this last year. Then we have some theoretical analysis performed by the theoretical group in materials department, and it's actually the slope, the higher slope in this material would be associated with so-called like more narrow bottleneck, which describes the interaction with phonons within lattice and hot carriers. So what can be done further is that since we have this setup, we have these facilities, so we can do visible pump, then we can push and probe with terahertz to measure directly, as we already had we have the information on concentration, but we can also study the mobility of carriers directly and compare optical probing with terahertz probing. And also we can turn to photocurrent measurement gated by terahertz radiation. So we have pump, then we have terahertz field applied and gate with the terahertz pulse and measure the photocurrent from the photovoltaic cells directly. And look into frequency-dependent, terahertz frequency-dependent time constants in carrier decay processes, and thus understand a little bit more about hot carrier dynamics in these materials. To conclude, I'd like to acknowledge the producers of the samples in Braunschweig University, computations done by JARV, and our collaborators working on the results I have presented in this talk, and Magicplot for providing a copy of the software. And thank you all for listening, and please ask any questions. Thank you.
Any questions?
No, we haven't looked into this, but this is in our plans. Like, first, we want to see, we would like to see the effect of terahertz onto photocurrent, where we measure the photocurrent from the device and use the terahertz to see whether it's changing the photocurrent or not. But we haven't looked into inverse process, because we just suffered another move of the lab, and we restored the lab. Just the beginning of April. It started working again, and hopefully we'll do this in the nearest future.
Okay, thank you. Any other questions?
Here.
Sorry, I didn't mention.
Yeah, actually all this work has been done within maybe within 1 year, which like 5 months of which we were not operating because the laser was in the move, or the lab was in the move. So it's quite preliminary results. Yeah.
So in your pump probe experiments, you observe different dynamics for different, let's say, wavelengths. And did you compare it, for example, to Raman spectrum or terahertz transmission spectroscopy? Because if it's phonon lines, they should be clearly seen there.
Yeah, this is what we're looking into now. We didn't do the thorough analysis, but we expect this to be we expect this to be phonon lines associated with phonon interaction, and longer times will be associated with phonon bottleneck that preserves the carriers from cooling down. yeah, this is what is expected, and that's why we see, like we noticed in that in cesium we have stronger interaction with phonons, and this is why the change of these characteristic times between the phonon lines and the other frequencies is so different in cesium lead bromide. Probably this
in
will
this
be,
case, they should strongly depend on the temperature. I mean, if you heat your sample,
yeah,
this dynamics should
this also should be really, yeah, this should be really looked into, and yeah, we're working on this temperature. We have cryostat, so we are going to see the temperature dependence as well.
Okay, thank you.
Okay, thank you very much. And also thank you for program chairing of this symposium. So let's thank speaker again. Okay, so and the next talk is given by Alexander Grebenchukov from ITMO University. And the topic is photoexcited terahertz conductivity in multi-layered and intercalated graphene.
Okay. Hello, and thank you for the introduction. Today I'd like to talk to you about the influence of the external photoexcitation on the optical and electronic properties of the multilayered and chemically modified graphene in terahertz frequency range. This is the outline of my talk. After giving you a brief introduction, the first part will be devoted to the experimental study of chemically modified and multilayered graphene by terahertz time domain spectroscopy technique, and then obtained experimental results will be described theoretically. Okay, currently, and as it's well known, there are many very interesting applications of terahertz radiation, such as spectroscopy, visualization, communication, biosensing. Moreover, the number of potential applications is still growing, and the progress in such an applications depends on the realization of cost-effective, broadband, ultra-fast components that could actively manipulate terahertz waves. There are many approaches to achieve this goal, and the promising one is to use the reconfigurable materials, such as two-dimensional materials, as a basis for the tunable terahertz components. In our work, we investigate the influence of the external optical excitation on terahertz properties of two-dimensional materials, and describe these experimental results by the theoretical model, and extract some parameters of the investigated materials. Here you can see the typical time domain spectroscopy setup with the external optical pumping source. And to obtain the complex conductivity dispersions, it's appropriate to use the effective medium model and thin film approximation using the following expression. In our experiments, we investigated 4 samples. They were multi-layered graphene on dielectric and semiconductor substrate, and few-layer graphene intercalated with the ferrum chloride, also on dielectric and semiconductor substrate. Here you can see the Raman spectra, which are provided to quality evaluation of the samples, and it's seen that multi-layered graphene has is low defectively, but after chemical modification, samples become more defective. So here the extracted conductivity, complex conductivity spectra for the chemically modified graphene on the electric substrate is on the left of the slide, and for the intercalated graphene on the semiconductor substrate. And as can seen from these dependencies, the real part of conductivity for the intercalated graphene on the electric substrate is almost independent on the intensity of optical pumping, while the imaginary part varies successively with increasing of optical pumping intensity. For the second sample on semiconductor substrate, there are changes both in real and imaginary parts of conductivity, but the values of the conductivity is low in comparison with the previous sample, which can be associated with the low quality of the sample. It's well shown on the Raman spectra. It's a green curve, so it's not very reliable results for the chemically modified graphene on silicon substrate. In the similar way, we obtained the conductivity spectra for the multi-layered graphene on also the electric substrate on the left and on the semiconductor substrate. Here the similar character of the dependencies. For the multi-layered graphene on semiconductor substrate, there is good tunability observed for the real and imaginary part of conductivity, while for the multi-layered graphene on the electric substrate, there is only good tunability for the imaginary part and not significant tunability for the real part of the conductivity. So for the further theoretical approximation, we use the multi-layered graphene on the electric substrate. It's on the left side of the slide. The correct way to describe the graphene is to use the surface conductivity, which can be calculated by using Kubo formula. It takes into account both contribution from the intraband and interband transition of carriers. The tunability achieved by adjusting the Fermi level of graphene. In our case, we use the optical pumping, and the relation between the Fermi energy and the parameters of the optical pumping source was described by that expression. Also, we consider that our multi-layered graphene has disorderly stacked graphene layers, so the properties of each layer was similar as the individual layer. We also took into account the attenuation of the pumping radiation from layer to layer, with the exception of the bottom layer. Its conductivity depends only on the interaction with the substrate, and there isn't any influence of the optical pumping on its conductivity. So thereby total conductivity of multi-layered structure, we consider it as the sum of the contribution of each layer, which is described by its own Fermi energy from top to bottom. So that is the results of our theoretical calculation on the right side, and we can see that the approximation definitely fit the experiment, and we can extract the parameters of our investigated material, specifically recombination and relaxation time, and the Fermi energy of the bottom layer. So, in summary, we investigated the graphene-based two-dimensional materials theoretically and experimentally. We demonstrated effective tunability of Terahertz properties by using external optical pumping of modest intensity. Obtained results was decently approximated theoretically, and we extracted some main parameters of investigated material. Thank you.
So, any questions?
Can you go back to the experimental results of the photoconductivity? Not modeling, but experimental. Yeah, multi-layer. What I can see here is that, and there was a question, and when you showed the modeling results, actually, I just wanted to ask it even more. The dependence of the imaginary part has different trend, like it drops down in on a semiconductor surface with higher pump, and it goes even negative, but it has a quite different dependence on a dielectric surface, and your modeling shows quite similar trends in change of this imaginary part of the photoconductivity. How can you comment on this? Can this be associated with silicon photoconductivity that you might have missed, or what can be the explanation, and why do you use the words of like the fit between experiment and theory, although the photoconductivity on the semiconductor behaves in a very different manner?
The situation for the multilayered graphene on semiconductor substrate is quite different, because there is a stronger influence of the substrate. And yep. The reference was the optically pumped silicon substrate. So that's
Did you take into account the change of Fresnel reflection?
I don't think so.
Maybe that's something you can look into, because the trend is quite obvious.
Yeah.
There are parts which is growing while it's growing in the electric, but in your theory you have similar trends.
Okay.
Okay, any other questions? Okay, let's thank speaker again. So the next speaker is Daniel Goleman from Whitmore University, and his talk today is optically controlled permittivity of single-walled carbon nanotubes for terahertz applications. Thank you very much. Let's thank the speaker. Questions?
I have two short questions. First is, why did you change this wavelength for pumping? And the second one is that you can see that under laser pumps you have higher transmission of terahertz, which is really untypical for all the photoconductive materials. How can you explain that effect?
Could you please show the transmission spectrum of your sample? No, optical transmission. Or absorption. Yeah, it's, I think, slide number 8 maybe. Or yeah, here. Actually, I have pretty similar question, because here you can clearly see that metallic carbon nanotubes are resonant with your pump wavelengths. And maybe this behavior is related not to semiconducting nanotubes, but to metallic. In this case, there is metal behavior of conductivity, like in metals. And can I ask one more question about, you showed that increasing the pump intensity, there is shift on the left side. What does it mean? Where it comes from? No. Yeah.
I think that we can continue discussion during the coffee break, because it's time to... Oh, you have a question, okay? Okay, again, I think that we can continue discussion during the coffee break. So let's thank speaker again. So now we will have a coffee break for 30 minutes, I think, and the next session will start at 11 o'clock.
So we're starting the final session of the Terahertz Symposium in the POEM conference. And there is a slight change of the program, and our first speaker will be Vladimir Antonov from Skoltech.
Thank you, Chairman. I have a privilege to give the same talk twice. So I had the rehearsal yesterday, but this time I will skip few slides now at the beginning. So I will talk about compact terahertz imager, and I will mainly talk today about array of detectors which we used for this imager. We fabricate these detectors in different design for quite some years, and this one, which I will describe today, is not so sensitive. I would say not world record sensitivity, but it's very robust. And I remind you idea that what we want to measure spectrum of some material. We cannot measure continuous spectrum if we want to have a remote system, because we do not have a powerful, continuous, tunable sources. But what we will do, we have some particular generators of terahertz radiation, which generate spectral lines, and we have a matched array of detectors. Each detector is matched to frequency of emitter. Emitter can be resonant tunneling diodes, and sensors I will describe in details now. So this is a system, array of detectors, emitters, maybe 20 or as much as you want. We send radiation. We detect reflected radiation by array, and then we amplify, condition, and send it to cognitive system to identify material. This is how it is look like. It's a compact cryocooler. At the finger of this cryocooler, we set up array, lenses. Array will be in a package with silicon lens, which focus radiation to array. It will be in a vacuum can, evacuated, and whole system looks like this. What is missing here, it is a Cassegrain optics. Obviously, when you have this optics, you have efficiency you increase as a square of area of this mirror to roughly maybe 3 millimeters of a channel, which is directed to an array of detectors. So it's about 3 orders of magnitude you can increase efficiency. So this is the array of detectors. So what we have a bow tie antenna, and in a focal point of bow tie antenna, we have a conductive channel. So it's a bow tie antenna is formed at the surface of a heterostructure, and somewhere 100 nanometers below surface, we have a two-dimensional electron gas. We cut conductive channel here out of this two-dimensional electron gas, and also we put metal gate on top in the form of in such a form of different sizes. So what we do, we apply negative potential to these gates, and we deplete electrons under these gates. So we have a source, drain, conductive channel, and we have two quantum dots on both sides of conductive channel. Operation of detector is relatively simple. When you shine it with terahertz radiation, you excite plasma waves into two-dimensional electron gas. These plasma waves rectified at the non-uniform potential close to the channel, and this potential affects, and this rectified voltage affects conductance of a channel. This is how, let's say, bulk to deck operates. It has a resonance feature, this absorption or excitation of plasma waves determined by the exact geometry of a channel, exact potentials. There is also two kind of, let's say, quantum dots which are formed close to the channel. They also, you can excite plasma oscillation in this quantum dot. Plasma oscillation is just vibration of these electrons as a whole. This plasma oscillations decay, and all energy of this vibration is transferred to a single electron. Electron will be excited from this dot, and dot will be charge excited. It means potential of this area will change, and this potential will affect conductance of a channel. So this is a kind of simplified explanation what happened in this device. So what we expect that close to the pinch-off of this channel, so this is a gate voltage, and this is the conductance between source and drain as a function of gate voltage. It goes to 0 when channel is completely blocked. Here we have nonlinearity, and close to this point, if we shine with terahertz radiation, we will see additional current or additional voltage, whatever you want. Here it's a photocurrent, so we have additional photocurrent. Sensitivity of this detector is about, in the best case, at 4 Kelvin, it would be around 10 to minus 17 approximately watt per square root of hertz. So it's relatively sensitive. You cannot detect individual photons, but you can detect at low temperature a bunch of about 10 photons absorbed by this to deck. And quantum efficiency itself of this device, it's a few percent. Right. Usually, effect is would be stronger if you have a two-dimensional electron gas with high mobility. So it's better to use gas with a mobility more than 100,000. Also, concentration is important because excitation of plasma waves would be better if you have a higher electron concentration. But concentration also affects the resonance frequency, which I will show you later. This device eventually operates on the principle of a so-called photoconductive floating gate, if you want kind of simple explanation of operation of this device. So in case of bolometers, what we have absorption of photon, excitation or creation of carriers, and we have a roughly 1-to-1 correspondence, 1 photon, 1 carrier. In the case of photoactive floating gate, or let's say FET transistor, we have excitation of some charge from some photoactive gate, yes, and this photoactive gate affects charge-sensitive device. So here we have eventually intrinsic amplification. In best devices, it can be amplification 10 to 6. So one absorbed photon affects current of 10 to millions of electrons. And we did quite different devices operated on this principle. My favorite is this one. It is if some of you know, there is a H channel in a two-dimensional electron gas. When you place two-dimensional electron gas in high magnetic field in a quantum Hall regime, then you have a H channel. In this particular case, you have only 2 Landau level are occupied, and top Landau level, it looks like a core. It will work this core as a photoactive gate, while low Landau level would act as a charge-sensitive device. So it's in the regime of Coulomb blockade. I maybe will not go further about this device, but it has a single photon sensitivity. It has a very nice property, and this device is used for low temperature terahertz microscope. And we use this device to detect, for example, cyclotron emission from a Hall bar to image position of H channel. What you can do, this device, it's a two-dimensional electron gas, this red one. It's a kind of scheme. And on top we have a gate, very similar what we have in our device, but instead of conductive channel, in our device here we have a aluminum single electron transistor. And single electron transistor is the most sensitive electrometer in the universe, and it detects change of potential of quantum dot when electron is excited of this quantum dot by, for example, absorption of terahertz photon, excitation of plasma oscillation, and then decay of this plasma oscillation with excitation of electron out of this quantum dot. So it's very similar to device which I described, but instead of single electron transistor, we have just conductive channel like it's shown here. Okay, plasma resonance. So we expect that because of this formation of these two dots, we will have a well-defined plasma resonance. If you model such a system, you have a metal, you have donors, you have a two-dimensional electron gas, sizes like this. So you will have a almost parabolic potential. And if you have parabolic potential, obviously you have a harmonic oscillator, and the frequency would be inversely proportional to size of this dot. For example, for dot of 0.7 micrometer, you have this resonance frequency. And it depends on carrier concentration. High carrier concentration, you go to higher frequencies, and larger dot, you go to low frequencies. So this is what we expect in our device. And indeed, if you look at the spectroscopy of such detector, you can see that there are some relatively sharp lines, maybe 10% of central frequency. If you change shape or change gates, then position of these lines changes. So this is what we did not, at the moment, we did not do systematic kind of design of these detectors. We're just happy that, for example, here we have a high sensitivity and we use this frequency. So responsivity of detector is about 100 volt per watt. So what is the problem with plasma system? That when you go to high temperature, excitation of plasma wave is suppressed. So this is the photo signal at 5 Kelvin. When you go to 100 Kelvin, then you have eventually drop of 2 orders of magnitude of photo signal. And as I already said, Terahertz system, which in the foyer, people, they did a measurement up to room temperature, and they had a 4 orders of magnitude drop of sensitivity. So when I saw this picture, I decided I should go to somewhere here. At least here we will, to let's say 70 Kelvin, we will have at least only 2 orders of magnitude drop of sensitivity. And this is why I bought this compact cryocooler and started to operate at this point. And maybe if it will be finally successful, we can use this system for more sensitive detection. Okay, so model of photoresponse is very simple. This is a phenomenological model. So you have a second derivative of current, and photosignal would depend on cross derivative by either gate voltage or source drain voltage, or here I think, yeah, beta would be induced voltage at the gate. And if we use this phenomenological equation, then we will see that eventually what is induced? It's induced voltage at the source drain, additional source drain voltage. Right. And if we think that it is a plasmon, then it should decay with temperature as a exponentially decay with the factor omega its frequency, and tau is the scattering time. So as we increase scattering time, as we increase temperature and scattering time decreases, then we should have an exponential decay. What is surprising that this nicely described up to about 20 Kelvin, but then we have a saturation of induced voltage. So it's unclear why it will not completely follow this exponential decay. And as a demonstration of operation, we placed lithium niobide sample, and we did spectroscopy, and we observed some absorption of lithium niobide. So now we will do more systematic study materials with in this frequency range accessible for us. We have a source for this frequency range just to prove, and then optimization of this system for to increase sensitivity, to add Cassegrain antenna, and so on. And this is what we need to do also. If you want to put it in a market, let's say, we need compact electronics, cognitive software to identify material, and here people who involved in this, this Professor Kamiyama from Tokyo University, it's our group at Royal Holloway, Alexander Tsalenchuk and Spas Spasov, Sergei Kubatkin from Chalmers University, my PhD student from Japan, and our technician with this system. Thank you.
Which one is this? Yes. Okay, we have some time for questions.
So you mentioned, thank you for presentation, you mentioned that you have 2 quantum dots, and these quantum dots operate like a single electron transistor, but why do you use 2, not 1?
No, they operate as a trap of photons, yes, and they operate as a photoactive gate. So they will be charge excited, and they affect conductance of a channel.
I see. Thank you.
Thank you for a very nice presentation. I have a small question. On the previous slide, you have the structure with parabolic potential. Could you please mention, comment, which was the structure like? Yes. Which kind of structure it is with the parabolic potential?
Okay, so what you can see is this is a top view, yes, top view, and this is a gate, metal gates, and we have opening like here, yes, opening, and here we have donors in gallium arsenide, and electrons are below donors, yes. So this is a full kind of model of heterostructure, yes. And 10 years ago, we did not have we did not have enough packages, so we just calculated this using Laplace equation and conform transformation. So this is the analytical solution.
Okay. Thank you.
Any other questions? I have a short question. You showed the results for lithium niobate reflection spectroscopy. I just wanted to ask, how long does this acquisition take? Like, how long these preliminary measurements, how long does it take to take the whole spectrum?
Whole spectrum, it's just determine how fast you can sweep.
So it's limited by the source?
Source, yes. So detector itself is relatively fast, so it's about millisecond. It's how fast you sweep.
Okay. Let's thank the speaker again. And the next speaker in this session is Rostislav Arkhipov from St. Petersburg State University. And he will talk about generation and shaping of few cycle exotic terahertz waveforms.
Раз, два, три. Раз, два, три. Thank you very much for the presentation. My name is Rostislav Arkhipov. I am from St. Petersburg University, and my talk is devoted to the generation and shaping of few cycle terahertz waveforms via coherent control of nonlinear medium. Just a few words about us. So this work is the results from the strong cooperation with our group. I'm working in the group of Professor Rozanov from Tmo University, and we strongly collaborate with the group of Professor Uwe Morganer from the University of Hanover. This outline of my presentation is here. Firstly, I will say a few words. Why do we need terahertz pulses? And everybody knows, but I just remind. So the second part is devoted to the generation of half-cycle terahertz pulses via unusual reflection of single-cycle pulse from nonlinear film. The third part is devoted to the generation of single-cycle pulse. And the final part of the talk, if I have time, I will say you a few words about generation of exotic rectangle-like and triangle-like terahertz waveforms. So terahertz electromagnetic range is between microwaves and infrared. Everybody knows this fact. And this part of electromagnetic radiation found a lot of application in ultra-fast spectroscopy of complex molecule, biological imaging, wireless communications and security, etc., etc. So all present days methods of terahertz radiation developed so far are based on nonlinear conversion of optical pulse in nonlinear medium. So the most common well-known methods are summarized here. It's optical rectification, four-wave mixing, ionization-based nonlinearity, and optically excited photoconductive switchers. But almost all these methods have some disadvantages in that they have low efficiency, 10⁻⁴ and 10⁻⁶, and the shape of the generated field is fixed. So high efficient terahertz waveforms development with controllable wave shape is still a complex problem. In this talk, we make the next step in the development of novel and high efficient methods of terahertz radiation with controllable wave shape. And we use another mechanism which differs from the commonly mechanism. We use the mechanism of coherent control of low frequency oscillations in nonlinear medium. So first of all, I will tell you about how to generate half cycle pulse via reflection of single cycle pulse from thin metallic or dielectric layer. In 2017, we published this paper, and we considered the reflection of pure single cycle pulse from thin layer. In this case, the electric field can be calculated using, so we consider one-dimensional propagation problem. And here electric field can be easily calculated by solving wave equation, which contains in the right side second derivative of the medium polarization in the case of dielectric medium, and first derivative of the electric current if we consider metallic film. So to calculate the field, we use standard green function approach. In the one-dimensional wave equation, the green function is the Heaviside step function, and the solution for the layer is that electric field is proportional to the second derivative of the medium polarization in the case of dielectric medium, and for metal film, it's proportional to just to electric current. So you see from this equation, that in the one-dimensional case, reflected field is proportional not charge's acceleration as in 3D case, yeah, it's proportional to the charge's velocity because it's the first derivative of the medium polarization, it's the electric current which is proportional to the electron velocity. And what happens in this case? The situation is very simple. When such pulse illuminates the film, the first half, positive half wave of the pulse just accelerate your electrons, and the negative half cycle of the pulse just stop your electrons. And therefore, the velocity of the electrons, it's just the half wave, yeah? And in the generated field, reflected field is just the half unipolar half cycle pulse. So could you please switch on the animation? Анимацию включите, пожалуйста. So this animation illustrates how it works. Moment. So here are our film. These are our metallic film, and this is the illuminating single cycle pulse. And now, in a few seconds, you will see that the reflected field is just half cycle unipolar pulse. Yeah. So yes, the reflected field is the half cycle pulse. So the idea is very simple. Сюда. Дальше, пожалуйста. Yes, thank you. The second method, which was proposed by us recently, is the generation of single cycle pulse, when the medium is illuminated by the femtosecond pulse train. So the basic idea of this method is illustrated here. We have nonlinear oscillators. We have nonlinear medium with nonlinear oscillators, and the electric field, the polarization is proportional to the square of the electric field, which is typical for the Raman active medium. And the first pump pulse creates the medium polarization, and the second pump pulse, if it arrives at the distance half period of the medium propel oscillator, it stops this polarization. And as a result, the polarization of the medium is just the half wave of medium displacement. Since the Raman active medium have resonances in terahertz range, we can generate, by this method, we can generate half cycle terahertz pulse. So what happens in one-dimensional case? If you have the thin film, we eliminate our film by the femtosecond pulse train, and the distance between these pulses is equal to the half period of the medium propel oscillations. The medium polarization is a half wave, yes? And as I said in the previous slide, the reflected field is proportional to the charge's velocity, to the first derivative of the medium polarization. The first derivative of the medium polarization, the charge velocity, is the single cycle sinusoid, yeah? Hence, the generated field is the proportional, has the shape of single cycle terahertz pulse. So now this figure illustrates this idea in detail. Here are the pumping pulse train, it hits the pumping pulse spectrum, we consider the pumping femtosecond pulses, which is typical for Titan sapphire laser pumping at 1 micron and duration 50 femtoseconds. And this and the generated reflected field is the single cycle terahertz pulse, which is illustrated in this figure. So in the numerical simulations, we use the layer which has thin 10 microns, and the resonance frequency of the layer is 1 terahertz. And generated pulse amplitude have the value order 10 power 4 volt per centimeters. So using this method, we can achieve the efficiency 10 minus 4 and 10 minus 3, which is very high. We consider one-dimensional problem. Now the interesting question arises, what happens in 3D case? In 3-dimensional case, at the distances far away from the medium, the electric field is proportional charge's acceleration, second derivative of the medium polarization. So this second derivative of this half wave, it's plotted here. You see that the charge's acceleration it's also have already the half wave shape, but it has also the tails of the opposite polarity. So it's not pure unipolar pulse, yeah? So, but the amplitude of this tail, of this negative tail, can be suppressed if we introduce in our medium some filter, some spectral filter. So in the further consideration, I neglect the influence of this tail, and I assume that we have this polarization in the form of this half wave. So how to generate? By using this idea, we can generate terahertz waves with some exotic shapes. We just need to introduce in our medium some delay. So if we introduced in our setup some delay, the half wave, which is emitted by each point of the medium, can come to the observation point with some delay. So if these half waves arrive in the observation point with some delay, we can generate some terahertz pulses with exotic wave shapes. So this figure illustrates this idea. From 2016 until 2018, we published several papers, which was done by our students, PhD students. And the idea is very simple. We have the medium, Raman active medium, which is illuminated by the train of 2 field cycle pulses with the distances equal to the half period of the medium proper oscillations. And the field is detected at the distances far away from the layer. So under such conditions, the medium is excited at superluminal velocity because the wave front, because the medium is limited at some angle, beta, to the medium. And the excitation, this cross-section point, moves along the medium at the velocity which is faster than the velocity of light. So each point of the medium illuminates such a half wave, and since the excitation velocity is faster than light, at the far field dawn, these half waves comes with some delay to each other. And this allows us to generate pulses with rectangular-like pulses with exotic rectangular-like wave shape. Here such pulses are plotted for the different values of the excitation velocity, and you can easily see that if we increase the velocity of excitation, the pulse duration also increases, but its amplitude goes down. This idea can be also improved if we introduce in our setup some diffractive optical element. Diffractive optical element, it can be the phase plate, which thickness or radius increases with the polar angle phi. So using such diffractive element, we can also introduce, we can create the delay in our setup, and also the half waves to the observation point will come with some delay. And this also allows us to generate the pulses with some exotic wave shapes. So here is the plotted the 2 examples of the emitted field for the different types of the diffractive element: spiral phase plate, which was plotted here, and also oxycon. Oxycon differs from this phase plate in that its radius also increases with the angle phi. And you see that you can generate both rectangular and triangular wave shapes. So I would like to remind that for the best of our knowledge, such exotic wave shapes were available only in radioelectronics. But this method allows us to generate terahertz, these rectangular-like pulses in terahertz range. So just opening the new perspective in the optoelectronics. So now it's my conclusions. So we propose several novel methods of high-efficient terahertz pulse production and studied them theoretically. We, in 1D case, we can generate half cycle and single cycle pulses, and in 3D case, we can generate exotic waveforms like rectangular and triangular-like pulses. So these ideas can be found in these publications briefly. So thank you very much for your attention.
We have some time for questions. I have a short question about your half-cycle terahertz pulse when you generated this. I think in the very beginning, you're using a single-cycle pulse to generate a half-cycle pulse.
Yes.
How do spectra of these pulses compare? Isn't this pulse also in terahertz range, lying also in terahertz range?
It can be attosecond pulse and can be terahertz pulse. It doesn't matter there.
No, but how would compare? How would the spectra of these pulses, of these two pulses, compare?
Of course, the spectrum of the half-cycle pulse is broader.
Okay. And the other question is about the generation of a single-cycle pulse.
Yes.
There's information about a medium. What kind of medium are you using here?
It's a Raman active medium. It has low frequency resonance.
Are there any real-life examples of this medium?
Crystals. Perylene crystal, it has a lot of resonance in terahertz range. Perylene crystal. Complex molecules.
Okay, thank you. Any other questions? Let's thank the speaker again. And next presentation will be given by Dmitry Sharavarov from Moscow State University. He will talk about vanadium dioxide epitaxial films for terahertz applications.
My name is Dmitry. I'm from Moscow, Lomonosov State University, and I would like to show you my presentation about vanadium dioxide in epitaxial films for terahertz application. So firstly, I would like to talk a little about vanadium dioxide and why we're interested with it. Firstly, between a lot of dioxide materials that shows metal insulated transition, the vanadium dioxide is unique because of its properties. The transition temperature of vanadium dioxide is close to the room temperature. For the bulk materials, it is about 68 degrees Celsius and occurs with a high resistance change in 5 orders of magnitude. For the bulk materials, it happens really fast, about 1 picosecond. And this transition can be triggered by temperature, by electric field, and the infrared radiation. Thin films of vanadium dioxide have some interesting features because in the mechanical properties they surpass the bulk materials, and the electrophysical properties are close to the bulk materials. I should point out that it is really hard to obtain high quality epitaxial thin films of vanadium dioxide because the region of the stoichiometric vanadium dioxide is really tight. Another oxides that vanadium can form with the oxygen have their own metal insulated transition at a different temperature and with different resistance at the low temperature phase and the high temperature phase. So it is well known that the phase transition of vanadium dioxide is the transition of the first order, and at the room temperature the crystal structure is monoclinic. At the high temperature we have a rutile type of structure with a metal type conductivity. not only these two polymorph modification vanadium dioxide can be formed in the experiments, but also another metastable phases for vanadium dioxide. It's phase B and phase A that are metastable, and the percents in the films have a negative influence on the electrophysical properties. So we have a solution for obtaining high quality epitaxial thin films. We did it by the chemical vapor deposition in the few steps. The first step was MOS-CVD deposition. We used complex substances of vanadium in oxidation state 4+, and steam of moist argon. As a result of the pyrohydraulic reaction on the hot wafer, we have a thin film of pure vanadium. This reaction showed here, and the structure of our complex substances is showed here. So the second step of our method is post-annealing at the 600 degrees. During this process, we recrystallize our film. We increase the grain size of the vanadium dioxide and reduce the grain boundaries in this film. So this is important because the morphology also morphology is also important on the electrophysical characterization of our films. So and the right part of the slide, you see our scheme of the reactor. Here I show some characterization of vanadium dioxide thin films. On the left picture, you see the temperature dependence of the resistivity of our films. If we skip the second part of our method, we will get the wide hysteresis loop of the resistance in the vanadium dioxide thin films. But if we did all the steps, we will get a perfect curve of the hysteresis. So after we obtained these good results for vanadium dioxide, we moved to the wafer scale samples. So here is the photo of a 2-inch sample of vanadium dioxide on the sapphire substrate. So in the different points, I show the thickness of the sample depending on the radius. So we see that there is no large difference between the center of the sample and the edge of the sample in the thickness. It was about 100 nanometers. The same is for hysteresis loop of the resistance. We have no difference between the middle of the sample, the center of the radius, and the edge of the sample. The same we have for the terahertz transmittance of vanadium dioxide thin films. Here we have hysteresis for 2 different samples without annealing and with annealing. We see that the hysteresis is wider for samples that have smaller grains and a lot of the grain boundaries than for the annealed sample. there is no also dependence of the radius on these samples, so we have almost the same changing in the transmission of terahertz radiation in our samples. Also, we did some structures on our samples. Here is the photo of our photolithography sample that we did on the 3-inch substrate. And on the bottom, you see the intensity distribution in the focus for these two focusing zone plates that can be used as a switcher at the same time. So on the cold state, we have focusing at the 50 millimeters and 100 millimeters for these two lenses. And at hot state, we have no signal in this case. So that's all. This is my summary. We propose a method of the producing of vanadium dioxide films. We show that we got uniform single-phase films of vanadium dioxide as the electrophysical properties is also uniformity, and there is no dependence on the radius of our samples. Thank you for your attention.
Let's thank the speaker. Some really nice results, especially about the lens. Any questions?
Thank you for presentation. May you go to back to the previous slide and look at the first figure. What curves depicts the results after annealing, and what curves depicts as deposited, because they look the same?
There's the same color, yeah. This white hysteresis is for the sample that was obtained without annealing, and here we see the hysteresis after annealing. So it is because of the morphology of our sample. We increase the grain size, we have a faster transition and lower grain boundaries that we have in the sample without annealing. Yes, yes. It happens because in the sample without annealing, we have some oxidation phases of vanadium, not the pure vanadium dioxide, but vanadium O2 plus X. So these phases shows the transition at the other temperatures. So if we combine them, we will have some kind of these hysteresis.
Yes, please.
May I ask a practical question? This switch is, did you see any degradation in number of cycles?
For the films, it's about 1 million cycles, I think. Of course, it depends on the thickness of the film. At the thicker film we have, the lower cycles I think we will get.
And what is the switching time?
It's a really good question because we did not make such kind of measurements, and we will do it in the close future.
Other questions? I have a short question about this intensity distribution and focus of your Fresnel lens. What kind of radiation did you use for this to measure the focus, and what was the method to measure the transverse profile of the focal point?
We used the radiation at the 3 terahertz frequency.
What was the source? Is it like a narrow band source, single frequency? What kind of source did you use for this?
It was a source of gallium arsenide crystal, we it was the pulses of the terahertz radiation.
So it was pulsed radiation.
Yes, yes.
But why are you saying that it's 3 terahertz?
It was pulses of
Narrowband pulses.
yeah.
Okay. Any other questions? Let's thank the speaker again. And our next talk will be presented by Anatoly Kvitsinski from ITMO University. It will talk about polarization properties of fuel layer graphene on silicon substrate.
Кого? Sorry. Good afternoon, the participants of the International Conference SPb-POEM 2019. My name is Anatoly Kvitsinski. I am a first-year graduate student at ITMO University, St. Petersburg, and my experimental research work takes place in the International Research Terahertz Biomedicine Laboratory. I would like to invite your attention to the topic polarization properties of fuel layer graphene on silicon substrate in terahertz frequency range. This work was carried out under the supervision of Mikhail Khadzitsky at ITMO University. Terahertz radiation is widely used in physics, astronomy, telecommunication and security systems, medicine and other fields of science and technology. But at the present time, there are no efficient devices for modulating parameters of the electromagnetic radiation at terahertz frequencies. One of the promising methods for solving this problem is the use of graphene as a functional medium in such devices, thanks to unique optical and electronic properties of these nanomaterials. And that is why an important and relevant area of terahertz photonics is study of graphene to devise efficient tunable terahertz polarization modulators based on them. And so our purpose of this work was an experimental study of fuel layer graphene using the terahertz time domain polarimetry to obtain its polarization properties. So, a fuel layer graphene on a silicon substrate and a silicon wafer as a sample of this substrate were chosen as experimental samples. This 10 layers graphene sample was synthesized at University of Exeter, UK on a nickel substrate by the chemical vapor deposition in quartz furnace and then transferred to a silicon substrate with thickness of 1 millimeter. Experimental samples were studied using the terahertz time domain polarimetry system. The main components of the system are the terahertz time domain spectrometer based on the femtosecond laser and a system of 2 paralyzers. To create external influences on the samples, an additional infrared laser for creating an optical pumping, and axially magnetized magnet for creating a static magnetic field were also installed. For each sample, temporal waveforms of the transmitted signal were measured.
the measurements were carried out in 2 stages. At the first stage, 2 paralyzers were parallel to each other, and at the second stage, they were crossed by 45 degrees. 2 such measurements are enough to calculate the Stokes parameters and fully describe the state of polarization of the samples. Experimental data processing was done using the MATLAB software. A coiflet-based denoising technique and boxcar signal windowing was used in this method. This technique allowed obtaining noise-free spectra in the range of interest. After that, the Stokes parameters and frequency dependencies of azimuth and ellipticity angles of the polarization ellipse of the sample were calculated. On the slide, the frequency dependencies of azimuth and ellipticity angles of the polarization ellipse of the silicon substrate in the frequency range from 0.2 to 1 terahertz. The solid line indicates data without external influences. The dashed line denotes the data obtained with optical pumping of 1 watt by centimeter squared and a magnetic field of 1.3 Tesla. It is seen that the joint use of optical pumping and magnetic field has the greatest influence on the angles. At frequencies from 0.6 terahertz, the amplitude of the value of the azimuth angle is more than 10 degrees. Similar results were obtained for graphene on the silicon substrate. Particularly interesting data from data is from 0.8 to 1 terahertz. The magnetic field has not so much a great influence on the results, as were described in the work earlier. Unlike optical pumping, which turns the azimuth angle relative to the point of origin, and the amplitude of the angle values is also about 10 degrees. These results indicate a large effect of the silicon substrate on the final data. For a visual compression of changes in the state of polarization of the samples under external influences, polarization ellipses at frequencies of 0.5 terahertz were calculated. The influence of optical pumping of the polarization properties of fuel air graphene and the increase in this effect when using an additional static magnetic field is especially notable. The changes in angles of the polarization ellipse might be connected with Faraday rotation effect. Applying magnetic field to isotropic material caused anisotropy, and as a result, a circular birefringence. Taking this into account, the vector of the transmitted linearly polarized wave is not the same as it was before the sample. So polarization angle rotation caused by Faraday effect depends on free carrier concentration, which can be increased by optical pumping, and the value of applied magnetic field. As a result of this work, frequency dependencies of azimuth and ellipticity angles of polarization ellipse and the polarization ellipse of the fuel air graphene on the silicon substrate and a sample of the silicon substrate were obtained experimentally using the Terahertz time domain polarimetry. The results show that it is possible to devise efficient terahertz paralyzers based on the free-layer graphene. The next stage of our work is the experimental study of polarization properties of graphene at different values of optical pumping at static magnetic field. The report is over. Thank you for your attention.
Thank you for interesting results that look quite novel. I haven't seen any much of those. And do you have any questions? Yes, please.
Thank you for presentation. Could you show the 9th slide? I'm just a little confused. The 9, yes. And the red is for graphene, yes, but the left is for substrate. So substrate also could be used as a polarizer, could work as polarizer. I didn't get it just. Could you comment?
About creating paralyzers based on silicon only?
Yes,
yes. Yes. Maybe, but so this peak at 0.8 terahertz, we don't think it is. It can be normal for. So we need more experiments with more samples of silicon because. Yes, it can be a Faraday effect, but we need to go deeper. So, okay, but okay.
We have any other questions? I have a short question. When you measure the transmittance of your sample under optical pumping with graphene and without graphene, you're not showing the transmission here. But in principle, do you observe higher transmission under optical pumping or lower transmission in terms of amplitude? You're not showing the amplitude, you're showing only the ellipticity. But in terms of amplitude, how does optical pumping of graphene changes the transmission of your sample?
So, about how polarization properties of...
Not polarization properties, but amplitude. You have transmission of terahertz pulses through your sample. And when you pump your sample with the infrared light, does the... obviously, I would expect silicon to become less transparent. But what happens if you have graphene on silicon? Does the sample become less transparent or more transparent? You don't have this data in your graph. I'm just asking because I assume that you have these experimental data and you may be aware. Was the transmission higher or lower?
Transmission of graphene?
Yeah.
Oh. Sorry. Transmission. Higher.
Higher. Transmission was better under optical.
Better optical.
So it's the same negative photoconductivity like in carbon nanotubes that were reported in previous talk.
Yes, and other part of our work is creating such paralyzers on carbon nanotubes and films.
Yeah, thank you.
Same effects under optical pumping and magnetic field, but no.
Okay, thank you. Let's thank the speaker again. And the last presentation will be given by Piotr Demchenko from my university and the study of complex conductance of bismuth nanolayers on various substrates.
Good day, my name is Piotr, and I would like to show you our work about studying of bismuth of different thickness and different substrates. As you know, Terahertz technology has more application in different areas. So there is a need for compact and effective cheap devices. And for this we are using some from these materials, but some materials have very big cost. Maybe these materials have very difficult fabrication methods, and we are focusing on bismuth materials, metal, and these alloys, because in Terahertz we found very low papers, and in these works we find very interesting results, and we decide studying nano-layer bismuth metal layer on mica, how very simply methods for fabrication. Fabrication was in Herzen University, and in Edmond University we observed on time domain spectroscopy of samples. We are using standard time domain Terahertz spectroscopy on transmittance mode, and we're using standard fast Fourier transform and complex refractive index and complex conductance for thin film methods by Sigman. In this slide we show Terahertz waveform which transmitted from materials medium, and we show that high peak shift in left sides in the time, and we show that pulse with increasing nanolayer of bismuth make a very strong left shift. And after fast Fourier transform, we show phase in spectra, and we can show that very low thickness of bismuth make increase phase relative air phase, and with increasing bismuth layers we have low phase difference and in negative phase difference. We calculated reflective index, and we how you show from 1 and 5 and 70 nanometer nanolayer of bismuth have refractive index lower than 1 on 0.3 and 0.4, and 150 nanometer layer have a negative refractive index in real part. In image part, we see increasing with increasing nanolayers. It's more. It's all right. Next, we calculated complex conductance, and we show with increasing nanolayer thickness, conductance increasing same. Image part of conductance decreasing. And we decide observe for different substrates and for same thickness, and we decide that we observed that in different substrates we get different properties of bismuth layer. So very big conductance in real part for mica, and lower conductance for PAT substrate. So we do show that with different increase in nanolayer, we get decreasing of reflective index. We can control reflective index from 1 to negative numbers, and for different substrates we get different properties. So thank you for attention.
Thank you. It was quite shocking results. Do you have any questions to the presenter? Yes, please.
We get because we get negative phase, because negative reflectance we mean poles. Well, we explained with substrate with nanolayer is like effective material. So bismuth have negative ellipse or permittivity. Mica have positive permittivity, and in these materials we have effective permittivity, and with the increase in nanolayer with bismuth, we increase in negative permittivity factor, and some.
So this is natural negative permittivity in bulk bismuth, in bulk nanolayer of bismuth.
I think yes, because for this nanolayer, for 150 nanometer, nanolayer become like bulk material. For 10, from 10 to 40, it's we can see some quantum effects, and from 44 to 100.
But did you see any other reports in literature of this effect in bulk bismuth negative permittivity? Did you check like overall literature? I can't remember, and I have seen some papers on use of bismuth for terahertz applications, but I can't remember any results reporting on negative permittivity. If you go to back to one slide back here, it's clearly seen that your pulse with bismuth, the orange one, arrives even earlier than the pulse that comes through the air. Is this an experimental fault, or it's the real effect? This is I mean, if it's a real effect, you have superluminal propagation inside the material. This is a big thing, but how exactly did you measure, and did you compare the time delay for these pulses?
Do you mean which results is in Noise? But we confirmed that it's real waveform, and
it's repeated in every next measurement. Like, did you?
Yes, we repeated a few times, and
what's the thickness of the substrate?
Thickness of substrates was 20 microns. It's very important. So
how did you fix the whole sample?
Fix it whole sample. Fix it of how we measure.
Yeah,
thickness.
when we measure, you fix, because maybe you have some effect that is related with moving along the focal spot of your setup. Did you confirm that you were placing the sample in the very same place?
Yes, we set up samples in focus in experimentally setup. Focus have very big shift, about 70. In 1 centimeter, we have focus in this setup.
1 centimeter transverse size.
1 centimeter of focus.
Like, okay.
Okay.
The beam waste.
Plus and minus.
Okay. Any other questions?
May I ask you a curious question? Tell me, circuits of distance is very complicated and interesting. Do you have any kind of idea how you can use this complicated circuits to make something extraordinary?
First idea for these materials is fabrication some coating materials, because not more materials have refractive index less than 1, and with material we can control refractive index from 1 to 0. Maybe in future we can develop it. That's all.
Let's thank the speaker again. Thank you all for coming, and hopefully we'll make it next year and make the same conference here. And you'll be welcome to present, and hopefully we'll have more people. And thank you all.
Now we have a lunch break till 1 p.m. 15 minutes, so I think it's around 1 hour, so you can enjoy your lunch.